let's get started. So last time we finished the all the sorting related stuff, as well as like the finding the ith rank. Okay, the order statistics. So today we are going to start a new topic, which is about hashing. Okay, so we have two lectures. Well, to be exact, like today we should be able to finish this one and the part of the second one. Okay, but probably not going to have be able to finish the hashing, completely. So next week, okay, we are going to finish the hashing as well as something else, okay, and that's it for the so there will be the material for the midterm, okay. So having said that, okay, I just want to remind you that the midterm is 2 weeks from now, right? Okay, middle of the April, which is April 15th, is that right? April 15th. Yeah. So so it will cover everything, until whatever we covered next week, okay? So what is hashing? Okay, say you have symbol table. Okay, we call the symbol table S, which holds n records. Okay, each record looks like this. Okay, you have a key. That is like what we want to, to use to access this record. For example, like I keep using this example. Like again, like in the payroll system, your ID, okay, it could be your key, right? So, but obviously, if it's payroll, it also contains other information such as your name, your occupation, your pay grade, all those things associated with your record. Okay, so we call that satellite data. Okay, and the operations we consider on this symbol table as include, you need to insert this, you need to be able to insert a record efficiently. You need to be able to delete a record from this symbol table efficiently. And also, obviously, you need to search a particular record from this symbol table efficiently. So how should the data structure S be organized? How do we, how do we store this symbol table? Okay, so because we have covered all the sorting stuff, right? So one obvious approach, okay, you could use a direct access table. In other words, okay, if your keys are in the range of 0 to n minus 1, okay, this is the range of your key. Okay, and the keys are distinct. For example, I just mentioned like the ID, right? So different people have different ID, right? So, which is nice. If that's the case, you know, you can set up an array, okay? You know, this array from 0 to n minus 1. So this is like the possible space for your key, okay? This size, the size of the possible space of your key, okay? And obviously, like, you know, you just use this array to store your record, okay? So, I mean, tk equal to x, if x is in this key set, and the key x equal to k, and nil, I mean, well, if this key, you know, has not, if this k has not been used. Okay, so that's a pretty easy approach. Okay, and all these operations, insert, delete, search, all these operations will take constant time because you just, you know, once you have a key, you can directly find the location of this record. Either you can do insertion, you can do deletion, or you can, you know, check if this record is there in this symbol table or not in constant time. So this is a very straightforward approach. But the issue is, okay, if you want to create an array, the size of the space of your key, okay, remember the key range can be very, very large. For example, okay, for 64-bit numbers, okay, it represents this many different keys. Okay, I cannot even pronounce it, but obviously it's a gigantic number. I mean, do you want to create an array of this size? Probably not, right? I mean, even if you count all the population in Taiwan, okay, it is only like a very small portion of this space, you know. So this is like a little bit overkill, okay. You really like create an array that is too huge for this application, okay. But you know, if your key is like you know, made of character strings, for example, we can certainly use the name as the key, right? If each record use the, you know, I mean, the person in the payroll, like we use that person's name. Okay, suppose like a different person has different name, then, you know, the character string, you know, it could be even larger because like, you know, here, okay, the previous one we consider like this 64 bits. Each digit is like, you know, it's just binary, okay. But if you consider character strings, then each digit is going to contain, you know, if you don't consider like uppercase, lowercase, it is already 26. Okay, not to mention if you consider uppercase, lowercase, that will be even bigger. Okay, and or if you consider, for example, like our ID. Okay, our ID. The first character is a letter, and the rest of, I think, 9 digits, right? So it's like you know, 10 to the power of 9. You know, times 26. That's still quite big, right? Like probably not going to be a good idea to use like the size of the array, you know, that huge, okay, for this purpose. Okay, so what do we do? I mean, the previous data structure that we talked about, no matter it's a sorted array, unsorted array, like if you don't use like the space of the key, okay, as like the size of the array, then somehow you need to, what should I say, like you put that your records into array, and you know, either you need to sort them, you know, put them in like a very tight format. You know, for example, if it's sorted, the insertion, because it's already tight, right? So you need, you know, if you find a place you want to find a place to insert it, and then for all the records, you know, behind it, I mean, they have to be moved one position to the right, so that you can clear up a space to insert this new record. So the insertion takes linear time. Deletion is similar, okay? Once you delete the record, I mean, all the records behind that will have to move one space to the left, okay? That also takes linear time. And the search, well, search, I mean, if it's sorted, well, it could be, you know, binary search, so it's log n, so it's not that bad, okay? But you can see that it's much more expensive, okay? If you still remember, so I mean, we also talk about heap, right? In heap, the insert, the delete, okay, can be done quite efficiently. I mean, basically log n. And the search, well, search is a little bit tricky. Okay, we usually do not consider search in a heap data structure. Okay, so the worst case, it could be linear. Okay, but anyway, just want you to understand all the data structure that we consider. Okay, for this operation, I mean, to build a simple table with these operations, I mean, are not that suitable, are not that efficient. Okay, and this one is just like the array space is too huge. It's not a good idea either. So here's like the idea of like a hash. Okay, so the hash function basically, okay, we call it like h. It maps the universe, okay, the space of like your key, okay, into a smaller space from 0 to n minus 1. So this is a mapping, okay. This U could be quite large. Of course, you won't have so many records there, okay? And you try to create a mapping from the subspace in U to a small, probably shouldn't say too small, but at least like to a table with a sufficient size, okay, from 0 to n minus 1. But this n minus 1 is much lower, much smaller than the space, size of the space of U, okay? And this mapping, I mean, just by looking at this figure, you will find that, okay, it may not be one to one. For example, you can see that key 5 and the key 2, they happen to be mapped into the same place, right? Right? Yes, that may happen. That may happen for in hash function. okay? So when a record to be inserted maps to an already occupied space in T, okay, we call that a collision. Okay, collision happens. Okay? So basically, okay, in this hash approach, okay, there are two centered factors to consider. Two factors to consider. The first one is the hash function. How to select a hash function? Okay, I mean you want to have a good hash function so that the collision does not happen like so often. The second, okay, when collision happens, how do you resolve the collision? How do you resolve the collision? So basically, the hash, approach basically surrounds these two different factors. Okay, once these two factors are determined, you have a hash scheme. Okay, so basically, just like insert, like a sorting, hashing has many different approaches. Okay, many different schemes. Okay, so but it's not like sorting, like it's so complicated. So that's why we only spend 2 lectures to discuss all the possible schemes in hashing. So today, the first focus is in the collision resolution. So when the collision happens, okay, one easy solution is you can just use what we call chaining. Okay, basically in the table, each record, okay, you actually store this record in a linked list. Okay, so if there's a collision, you just put it, into this linked list. So, for example, in this particular example, the hash function of 49 and 86 and the 52, these three numbers happened to be mapped into the same location I. So that is the reason we have this linked list. Okay. So so this chaining is an easy resolution for collision, obviously. Okay. So how about access time? When I say access time, I'm talking about those 3 operations: the insert, the delete, and the search. Okay, so insert. Well, if in the worst case, if all the records are mapped to the same location, remember we need to consider the worst case scenario, right? In algorithm, okay? So if all the records, all these records are mapped to the same location, so your symbol table will be reduced into a long linked list, right? So in the linked list, okay, the insertion, if the insert happened at the end of the linked list, well, it will take linear time, right? If you want to insert at the beginning, that takes constant time, yes. But if it's like truly rare to the end of the linked list, that takes linear time. Deletion, well, you need to find, you need to identify the record first, right? So, well, deletion basically like it's kind of like you need to search the record and then delete it. Okay, so the search. So let's first talk about search. Search. Well, you need to go through this linked list to find your record. Okay, so that takes linear time. Okay, linked list cannot use a binary search. Not to mention, these records are not sorted. Okay, so yeah, I mean it's a linear time. And then if you want to delete that record, that takes another constant time. So basically, the insert could be constant time. The delete and the search take linear time. Okay, if you use linked list. But if that's the case, then you lost the advantage of hash function, right? But of course, that is assumed this is the worst case scenario, right? This is worst case scenario. I mean, if all the records are mapped to the same location, all the keys are mapped to the same location, okay? Or many keys are mapped to the same locations, okay? If that happens, this is bad, okay? So, that's why we also need to consider the property of this hash function, okay? We make the assumption of simple uniform hashing, okay? What is simple uniform hashing? We assume each key is equally likely to be hashed to any slot in table T, independent of where other keys are hashed. Okay? So this is like the assumption we have for the hash function. I mean, remember I say like we will have to talk about the choice of the hash function and the collision resolution, these two factors. So this is of course this is this means we need to be able to find a good hash function, okay? At the end, you will find that this simple uniform hashing property is very, very difficult to achieve. Okay, or maybe put it this way, it's much more complicated than you may think. Okay. So let n be the number of keys in the table, and n be the number of slots. Okay. Usually, n is bigger than n. Okay. First, you have to have enough space to put all these records, right? Otherwise, your table, no matter how you deal with it, the table will be full, right? Assuming your table, you do not use linked list, okay? Assuming each slot in your table, has a record. You put a record, okay, or unoccupied, okay. So each slot in the table, okay, is used for one record, okay, only. if that's the case, obviously the table size has to be bigger than the number of records. Okay, so n is bigger than n first. So we can define a concept called load factor of t. Okay, it's very simple. Okay, basically it's n divided by n. We call it alpha. Okay, it's load factor. We call it alpha. So basically, it represents the average number of keys per slide. Okay, very, very simple idea. With that, it will help us in the following analysis. Keep that in mind. So first, it's about search cost. Okay. So what is the expected time for an unsuccessful search for a record with a given key? So first, you need to calculate. The hash function, right? Like computing the hash function take a constant time. So that's where your 1 comes from. Okay? And the alpha, this alpha cost is the cost for the search. Okay? But how do we analyze it? The expected search time is constant. If your alpha, the load factor is like a constant, okay, it's bounded by a constant, okay, or equivalently, if n is like can be represented as like a linear, order of n. So a successful search has same asymptotic bound, but rigorous argument is a little bit more complicated. So you can check textbook. So here, you could try to, why do I say search the list? We are talking about something like this. Okay. You may be able to go through the list to find this number, but find this record. But the chance to go in this record, in here to find the record is alpha. Okay, so that is why this is the expected time of unsuccessful search. So then, okay, it comes to choosing the hash function. Okay. We are going to talk about two basic hash function choices. Okay, two different basic hash function choices. Okay. In the next lecture, we are going to talk about some advanced hash functions. Okay. So right now, okay. So we are going. So this part is about like the simple hash functions. Okay. The simple hash functions. Okay. As I said, okay, the simple uniform hashing is very difficult to guarantee. Okay. There are two ways that we can not like achieve this property, but it's going to be close, okay, close to the result will be close to this the property that we design, okay. So good hash function should distribute the keys uniformly into the slots of the table. And also we know regularity in the key distribution should not affect the uniformity, okay? What is regularity? Regularity means that if you have certain patterns in your key, that pattern should not affect the hash function to make like the result to be uniform, distributed. Okay? So there are two basic hash function selection. The first one is what we call division method. The second one, obviously, if you have a division, the second one must be what? Multiplicative method. Okay? So, let's first talk about division method. Okay? Assume all keys are integers. We define hk equal to k mod m. Okay? So this is a very, very simple key selection. Okay? So, although I think you guys have taken discrete math, right? Discrete math talk about some the congruence, those type of mathematics, right? So, first, if you use this way to compute your hash, your n, probably, you should not have, the n probably should not have a small divisor, d. Okay. If the n has a small divisor, d, you will find that this hash function will result in collision very easily. Okay, very easily. You can come up with some of those by yourself. For example, say you choose even number as n, which obviously means you have a small divisor d to be 2, right? Okay. For example, you use 6, and then you can try different value of k, and you will find that a lot of a key, after the hashing, they will go to the same value. Okay. In other words, collision. Okay. So usually you could pick n to be a prime. If you remember what you learned from from discrete math, picking n to be a prime has some advantage. Okay, because different keys are more unlikely to be mapped to the same location, unless they are congruent. Of course, if they are congruent, you have no way to avoid that. But as at least, other than that situation, there's no way two keys will map to the same location. Okay? We are going to talk about that in more detail. Okay? So, another thing you should avoid, okay, if n is 2 to the power of r, that's the very, very bad situation. Why? Because the hash doesn't even depend on all the bits of k. For example, say that your the keys looks like that, and r is 6, so it's like a 2 to the power of 6. Okay, n is 2 to the power of 6. If you do like a k mod n, which is 2 to the power of 6, you know like only the last 6 digits will be used, right? So that's like the result is going to be 011010. Okay, so that is what we say, like it doesn't depend on all the bits of k. Okay. So that obviously, again, will easily create like a lot of collisions. So as I said, you could pick n to be a prime, not too close to a power of 2 or 10, and not otherwise used prominently in the computing environment. Okay, so basically a large prime, not too close to a power of 2 or power of 10, okay, will be a good choice. Okay, but that's usually what we do for the division method. But there are also some issues here. First, obviously, if n is a prime, that means that implies your hash, your symbol table is of size, of a prime size, right? Because your symbol table is of size n, right? Now we say like n is a prime. Then the symbol table, we usually, when you declare a table, the size is really a prime. Okay, that makes your symbol table a little bit, what should I say, like awkward. Okay, awkward. We usually use like, for example, say like maybe 1,000, something. Basically like a very straightforward number. Okay, that's like the first consideration. The second consideration is actually what should I say, like more important. That is why we need to consider the second approach. Okay, like a division, especially when you need to divide your key, which is it could be a large number, by a large prime. It takes some time, right? It is like considered a more complicated operation, right? Okay, so you want to, because remember, this hash function, obviously, because it's used to access like elements in the symbol table, so this hash function will be called very, very often. So you need to do this computation all the time. So you want the computation to be done efficiently. Okay, so dividing a large number with a large prime, it doesn't sound very efficient, right? That's the issue. Okay, that's also like something we need to consider. Okay, so that's why we consider the second approach, multiplication method. Okay, assume all keys are integers. Okay, and n is 2 to the power of r. Remember, this n represents the size of your table. Okay, so 2 to the power of r, well, it's a much better setting, right? At least the size of table is no longer a prime. Okay, and our computer has W bits, words. Okay, so depending on your computer, okay, it could be 16 bits, it could be 32 bits. Okay, why do we need to consider that? It is because this type of computation can be accelerated, okay, by hardware. Okay, if you try to design it carefully. Okay, so since we talk about like hardware acceleration, so we need to consider like some factors in hardware, such as like the length of the word in your computer. Okay, so we define your hash function hk to be k times factor a, okay, mode 2 to the power of w, rsh w minus r. Okay, so what is this? It looks complicated. Okay, so RSH represents the bitwise right shift operation. Okay, so A is an odd integer in the range of 2 to the power of w minus 1, okay, to the power of w. Basically, it's larger than half of the word. Larger than half of the word, and smaller than, so it's somewhere like larger than half of the word. Okay, and it's an odd number. Okay, so you don't want to pick A too close to two ends. Okay, and then this multiplication modulo 2 to the power of w, okay, can be done very efficiently, right? Again, you should learn this type of calculations in your discrete math, right? Multiplication modulo a certain factor, a certain number, okay? Because basically you can do modulo, okay, on both ends, and then multiply them. And this thing can also be done like iteratively. Okay, so which is a very nice. It can speed up the computation basically. Okay, so this computation could be fast, could be much faster than division. And then what is RSH? W minus R. Okay, let me use an example. Okay, let me use an example. Suppose M is 8. Okay, so your table is 2 to the power of 3, this size. That's the size of your table. Okay, and then your computer has like the word, okay, is 7-bit, okay, 7-bit. Of course, I know like no computer is designed with 7-bit word, but bear with me, okay, just assume that this is the case. Okay, then let's assume our A is like this. So you can see that it's bigger than half of the word, right? Because you have the first digit to be 1. Okay, so it's bigger than half of the word. And second, it's a odd number. It's not an even number, right? And it's somewhere, it's not close to a 2 to a power of w minus 1. It's not too close to a 2 to a power of w. Okay? And then, okay, let's say this is A. So multiplication will result in like this. Okay? So modular 2w. So first, modular 2w will, it means like, you only have the last 7 bits, right? To here. Because you do like a modular 2w, right? So what is RSH w minus r? Basically, that means you want, okay, here like r is 3, by the way, r is 3. Okay, basically like 2 to the power of 3, 2 to the power of r. Okay, that is n, right? 2 to the power of r. Okay, so basically that means you want these few digits, the leading or the most significant r digits from the module. Okay, that's it. So obviously this can be done very efficiently, right? Just like do like just a shift operation. So first, this part, it can be done, it can be computed efficiently. This one can be computed so efficiently. So that is why this multiplication, hash function, is preferred, okay, over the division method, usually. The division method, of course, it has its advantage in the sense that it's easier to understand by human. Okay, but if you consider implement into like a program and expect like a computer to be able to compute efficiently, then multiplication method is usually faster. And you may argue, well, then because we do, mode 2 to the power of r, then isn't that going to rely on the last few digits? You may argue, okay, well, we just mentioned like, this, if n is 2 to the power of r, it's a bad choice, right? So why do we use like mode 2 to the power of r in the multiplication method? That is because, okay, in the previous one, we do k mode 2 to the power of r, right? Here. We do k mode 2 to the power of r directly. But here, we do a times k mode 2 to the power of r, w. Okay? If you multiply your key with a, then it is not going to be that easy anymore. Okay, it is different. It's different. Okay? And you can represent like this thing by a modular wheel, but I think that this is like just by looking at this example, it should give you a very clear like intuition already. Okay, I mean using this illustration, I don't think that will help you in any way. Okay, so basically like you just need here your HK is 0, 1, 1. Okay, which is 3 actually. Okay, so if I, for example, in the exam, I give you like your A, your R, and your word length. Can you compute anything? Shouldn't be too difficult, right? Yeah, it's just very simple computation. Okay, so let's take 10 minutes break. We will come back. Okay, we are going to discuss like the collision resolution in greater detail. Okay, so no, 存钱。